All right, so we're going to be digging down into the CPU and to the guts of the computer. We're going to talk about binary and decimal and how that relates to what we're doing. So let's dig in. When a person types something at a keyboard, they might type in an A or a $sign or a pound sign. Well, eventually it gets to the CPU, and as you saw in the last video, CPUs don't really understand the letter A or the letter Z. All the CPU understands is impulses of electricity. If a circuit has an impulse of electricity, it's on, and then if it doesn't have any impulse of electricity, it's off, just like a light switch. And so that on and off pattern is what the CPU reads, and we call it 0 and 1, but all it is the absence or presence of an electrical impulse. So how do we get from A or Z at the keyboard to a 0 or 1 that the CPU can understand? So these little guys typed in an A, and what happens is we have this little ASCII chart, and I'll show it to you in the next slide, but understand that an ASCII chart is sort of a secret decoder ring. It's what we as humans have agreed that a certain letter, let's see, here's our letters, or a certain symbol, any of these symbols will have a, symbols here, symbols here. Symbols are the char column. Any of those char columns, any of those symbols have an equivalent representation in decimal or hex or binary. So I can't really relate how an A gets related to a binary, but I certainly understand the secret decoder ring when you tell me that, for example, A is 65. And we'll look at this chart here in a minute. But for now, what happens, we'll just kind of get the overall concept, is our little compiler or an interpreter will read our letter for our language, and then translates it into, it looks it up on the secret decoder ring, and here he sees that a capital A is 65. So this little interpreter or compiler will convert that 65 into binary for us, series of zeros and ones, a series of off and on switches, and send that information to the CPU. So let's look at this little ASCII table. There it is, just a little bit more up close. So this is just a chart that humans have created that we have agreed that an A will be represented by the number 65, etc., etc. We call it the ASCII table, which is American Standard Code for Information Interchange. I will admit that I didn't remember what that is. I had to look it up for this video, but I remember ASCII very simply. ASCII is used a lot for decoding what you and I see as characters, or these also could be Japanese characters or Chinese characters. It doesn't have to just be the English language, but this is what the part of the ASCII chart that we're looking at. And there's a conversion. And you'll notice that, for example, capital A to Z is always 65 to 90. And then our lower A to Z starts from 97 on the way up to 122. So it's really not that important for this class to remember all of that. But what I do want you to get this concept of is this ASCII table and how it does translate from a character to a decimal, and then from a decimal onto a 0 or 1, which, let's talk about the terminology. Bits and bytes. So a bit, short for binary bit, is just that single digit, on or off, 0 or 1. So a bit is just a single 0 or 1. It doesn't represent a character yet, or a number. A byte is a grouping of 8 bits. So now we're seeing 8 bits being grouped into one byte, which is 8 bits, series of zeros and ones, on and off. And it turns out that a byte is what holds our character. So our characters are held in a byte, which are 8 bits of zeros and ones. So A was 65 in decimal. That got converted into this interesting number, series of on and off impulses for binary. So let's look at how that conversion works. All right, this should look familiar, hopefully from some point in your life you've dealt with powers of our decimal system. In our daily lives, we deal with this decimal base 10. And what that means is that if we were to look at these are placeholders, right? So if we have something that's 10 to the 0 power, that's equivalent to 1. That's the first first column. If we have something that's 10 to the 1, that takes up 2 columns. That's the second placeholder in our number. So this is the tens place, zeros, ones place, and the tens place. If we have 10 to the 2, that's the hundreds. 10 to the 3 is 1,000, and on up to numbers that I'm not going to even pretend to tell you that I remembered right now. But I think you got the idea. This should look familiar. Well, it's exactly the same thing in binary, except we're talking about binary base 2, which means that our base number is 2 as opposed to our base number being 10. So now if we look at 2 to the 0, well, 2 to the 0 is just like 10 to the 0. That's still 1. 2 to the 1 is 2. 2 to the squared, 2 to the power of 2 is 4. 2 to the power of 3 is 8. And on the way up the chain till we get 1 byte of characters, or bits, 1 byte of bits, which is 128, would be our highest value. So let's see how that translates. So if I look back at the number that we were just talking about, we said that 65, which was the capital A, is 010001. What I'm going to do first of all is take a binary number and we're going to convert it into the 65 so we can see how we got that. So what I'm doing is just simply placing, just like we would have placed a 5 and a 6 here if this was a base 10, I'm placing all of those numbers in each pocket of our base that we just set, base that we just set up down below. So if we look at any of these placeholders that have a value, in other words, there's a 1 in here, so there's a light on. So this represents the value 1. 2 to the 0 is 1. This is 0. This value is 0 because there's nothing here. There's no value being held. 0 is 0, so this doesn't apply. There's nothing here, there's no value here, there's no value here, there's no value here, there's no value here. There is a value here. And this placeholder is 2 to the 6th, which means this value is worth 64. And then again 0. So if we then add up the values that had a impulse or an on switch or a 1 in it, we add 64 plus 1, we get the decimal of 65. So what we're seeing here is how we can turn a decimal, or excuse me, a binary into a decimal. Let's try another example. Okay, what is the decimal value of 0000011? Well, let's see. 2 to the 0, there's definitely a value there. So 2 to the 0 is equal to 1. There is a value here, so 2 to the 1 is 2, 0, 0, 0, 0, 0, 0. So 2 plus 1 is 3. So this is the binary representation of the decimal number 3. Okay? Let's try one more. Oh, how about this one? So all of these have a value in them. All of them have an on switch in them. So let's add all of those up. 2, 4, 8, 16, 32, 64, 128, and if you add those all up, you get 255. So in this video, we've seen why we're concerned about, or why we're interested in turning decimal values into binary. That's how we get from a letter A or a letter G on our keyboard. Our little interpreter or compiler translates that character into binary, and then from binary sends that on to the CPU as a series of on and off switches. We've discovered that a bit is a single digit, and 8 of those bits is a byte, which contains our coding for each character or symbol on our keyboard. And then we watched how we can convert a binary number into a decimal number. So in the next video, we're going to watch and see how we can turn a decimal into a binary number. See you there.